Good morning, good afternoon, good evening, wherever you are listening today. My name is Steve, and I'll be taking you through the second in this series of high voltage DC seminars. The first one we had last week was a general introduction to high voltage DC. We talked about Tesla and Edison and a poor unfortunate elephant named Topsy. We talked about some of the advantages of high voltage DC versus AC systems. A brief look at two of the components, which we'll cover in more detail today in this deep dive, and then a very high-level look at some of the markets and applications in which high voltage DC plays a major role. We do have an update on those market-specific seminars later with some guest stars from HP and Universal Skyline taking part. The previous seminar, the introduction, has been recorded. It's currently being formatted, and it will be on vicorpower.com by next Friday, the 20th of December. So as part of high voltage DC for Vicor, we look at a power component methodology. This means that we have different functions, whether it's a regulator or a transformer, which are building blocks for larger systems. So much in the way that Lego is a system made of small building blocks which are replicated and can be used in many different links or formations to form different systems. So we look at optimizing each of the small individual components, those power modules, and then arrange them in different ways for the different systems. Physically, those devices are highly integrated electronic components. They have multi-layer PCBs with planar magnetics and then active FET silicon and also analog and microcontroller ICs, plus a bunch of discrete light resistors and caps, which are overmolded to form a nice smooth surface if heat sinking is required. And the overmold also acts as a heat spreader for any hot spots within the devices. Since 2003, we've had the VI chip family, which are the full chip and the half chip you see there, roughly 1 inch area or a half-inch area. And at APEC this year, we launched the technology for a new family called the chip platform, which features advanced magnetics and an advanced structure for higher power density, higher efficiency, and also lower price points. As we go through this technical seminar, you will see the further reading elements at the bottom. So when you look at the recording of this, you will be able to click or access these links for further information. Some of these are technical white papers that we had accepted at IEEE conferences like APEC. Others are Vicor white papers, or also some magazine articles which help to describe the concepts further. So the first of the components today is a non-isolated buck-boost converter. So here we have an arrangement of 4 switches around a central inductor, and the pattern by which we turn those MOSFETs on and off takes power from one side of the device, the left-hand side, to the right-hand side, and we can adjust the voltage or regulate that voltage up, down, or keep it steady. So this is our non-isolated regulator. It's zero voltage switching, and we'll go into the details of that when we look at the waveforms, which means that we can turn the devices on and off very quickly, which means we can improve the frequency of the device, which means we can have higher performance magnetics and a smaller size, less parasitics in the circuit board, and a continuing positive cycle of features which result in very small, very high efficiency, very power dense building blocks. The buck boost operates in what we call a universal engine cycle, in that the sequence of MOSFET switching is the same regardless whether the device is bucking, boosting, or simply passing through power. It is the timing of those elements which vary, and so give us our buck-boosted or pass-through results. In terms of products, the VI chip, full chip, that's the 1-inch area, we're now up to 500 watts in that single device as a regulator, up to 97%. Looking forward to the chip technology, we should hit 1 kilowatts in a device which is about 1.5 inches area. So now looking at the PRM, there are 4 distinct phases of operation, each of which are linked by a zero voltage transition. So the first one is the input phase, where we have Q1 and Q4 turned on. We have an in-to-out phase where that voltage is matched left to right, obviously using the inductor to transmit the power it has within it. There's a freewheeling phase where we've got Q2 and Q3, and then we have a clamp phase. The clamp is responsible for limiting the amount of negative current that we have in the switching cycle as we pass through zero, and you'll see again in more detail. It's important to note that we do cross the 0 point or return to zero in each of the universal cycles. Therefore, this is a discontinuous mode device as distinct from continuous mode converters. So in terms of the boost mode, this is where we have a low voltage on the input going to a high voltage on the output. We're looking here at the voltage and the current on that main inductor in the center. So in the input phase, we turn on Q1 and Q4, and in this boost mode you can see there's current going through that inductor. And at this point, we go into a zero voltage transition where we turn off Q4, and the inductor wants to keep passing that current to the right-hand side, and the result is that the voltage on the point between Q3 and Q4 increases to match the output. Therefore, that's a zero voltage across the MOSFET of Q3. The input to output phase means that we move the Q3 on now, so we have a matched Q1 and Q3 output. And you can see also in the boost mode that the current through that inductor is decreasing. And this is the main difference between the buck boost and buck boost modes, is that there's obviously a duration of switching, and also that current slope during the T2 phase is a giveaway about the buck boost or buck boost format. Again, we go through another zero voltage transition, which allows us to have Q2 turn on in a zero voltage switching manner, and now we have a freewheeling phase. Obviously, power again continuing to go to the output, and also now notice that the current goes to zero. Again, this is the discontinuous topology. We go through another zero voltage transition, and notice the current is now slightly negative, and this is because we now clamp that current, and that is the restart for the whole cycle. So that's the clamp phase on the negative. Go through a final ZVS transition, and we're back to the start. So that was the boost mode. Noting the slope of the current during T2, and also in the boost mode, notice that T1, we spend a lot of time in that T1 phase, which is Q1 and Q4 turned on, and in the boost phase in T3, which is the free wheel stage, a very short time in Q2 and Q3. When we look at the buck boost mode, where the input is very close to the output we desire, you'll see the same switches transitioning, same ZVS stages, but notice that two things. One is that in a buck boost mode, the current remains steady during the in to output phase. And obviously you notice also, because we've matched the input to output voltages, there is no voltage across the inductor, so that is at the 0 point. Again, we go through a ZVS transition, which allows us to turn on Q2, and we have a symmetrical current waveform due to that symmetrical in to out voltage. Same thing applies with the ZVS transition. Same thing applies with clamping the current at a very small negative value. Again, a final ZVS transition, and we restart the clock. So the buck boost mode is identified by the steady current during T2 and also the even timing of T1 and T3. So a very even sharing of the load across the different MOSFETs in the device. When we look at the buck mode, again, same input phase, same Q1 and Q4 on, but notice a very small time duration. And then after the ZVS transition, the current across that inductor continues to rise. So here we are, we're bucking down, so the input is higher than the output, and you can see the continuing current flow there. Notice obviously that we have now a positive voltage across that inductor for the voltage. Same ZVS transition, same kind of freewheeling phase, but you notice an asymmetrical current waveform. Same kind of negative current, same clamping, and then same return back to the start. So here you'll notice that in the buck mode, we have a very short time in T1, which is the Q1, Q4 transition. In the T2, which is our in-to-out mode, we have the increasing current. Then the freewheel stage of T3 is very long for the buck example. And then the clamp is the same for all of the different buck boost or buck boost scenarios. So this is a brief run-through of the switching cycles of the buck boost non-isolated converter. Turning now to the second device of our chipset or our Lego blocks. Now we're looking at an isolated and fixed ratio transformer. So the topology is called a sine amplitude converter, and it's a full bridge in this example with an isolated transformer and then full wave rectification on the secondary side. In this topology, we have full zero voltage and zero current switching, which means that we can continue to optimize the efficiency of the whole device due to the fact that we don't have to deal with any trapped gate charge or other parasitic elements within the MOSFETs. So this is a real transformer. The device is made of, again, the high layer count PCB. The layers of the PCB act as the primary windings. So we go around and down, around and down, around and down in the PCB with the planar magnetics either side, and again the active silicon to control the current. In this case, we can consider this device to be a DC to DC transformer. So DC power is applied on the left-hand side. We use the MOSFETs to switch into a sine wave which crosses the transformer gap, and that sine wave is full wave rectified back to DC. A few things to note about this, one of which is this is a minimal energy storage. It is an LC resonant device with a very small L and very small C. In fact, the L is the leakage inductance of the transformer, and the C is a small bank of chip capacitors within the device. This is also a fixed frequency resonance system, unlike most systems which have a dither around the central frequency. So it's very easy for us in this case, with a high frequency primary, that 1.7 megahertz, for example, to have very high frequency, which helps us with our magnetics, which helps us with our efficiency and the small size. Note also that because we're doing the full wave rectification on the secondary, that 1.7 megahertz on the input becomes a 3.5 megahertz ripple on the output. So it's a very small amount of ripple and a very high frequency, which means that this device, whether it's input filtering or output filtering, is very easy to do, very small, low-cost components. We also have a 2x overpower capability of this device, which we'll come on to later, which really means you can optimize how many converters you need in a particular circuit for cost and size. Several versions are available, and in the classic full chip version, that's the 1-inch area, we're up to 330 watts in that small device. In the chip form factor, which we'll be releasing in the next couple of weeks to full production, we'll be able to get up to 1.5 kilowatts in a device which is only 2 inches in area. And again, more information, we actually have a video that's online on the website to explain this. So when it comes to the circuit, this example will go through that there's a full bridge primary with that center tapped secondary. And as we go through, note that we are looking at the voltage and the current on the primary side. We're looking at the voltage on the output and also the secondary side current. So those are the elements that we'll look at as we open and close our switches. So to begin with, we've got Q2 and Q3 closed. You see the voltage across the primary transformer and the current going in its half sinusoid. And again, that output current has the same sinusoidal waveform, or the secondary current rather, and the Vout obviously is rectified to a certain DC value. When we switch those devices, so we've now got Q1 and Q4 turned on following a zero voltage transition, you can see that the primary current is a full sine wave, secondary is a rectified sine wave, and the Vout, notice, stays at that DC value, but it does have a small ripple. And as we go through, you can see the primary current is the sinusoid, and that output voltage continues with a frequency which is 2x the primary. So this is the operation of the sine amplitude converter with a fixed load. However, the name sine amplitude comes from the behavior of the system when we go through a load step. So here we've added a load to the right-hand side, and we start the first few cycles with our standard load applied, and you can see the standard voltage and current on the primary, the output voltage and the secondary current, the same as before. But now we're also putting a measurement on the load current itself, and you can see we're at a nominal load. When we close that load switch and increase the load, you can see that increasing, we have a commensurate increase in the amplitude of the primary current. You notice the sine wave increasing. That continues to increase, and then within a few cycles, because we have a very fast switching device, we have a stable waveform again, but the amplitude of that primary current has increased. So this is the sine amplitude converter, where the primary current increases with the load current. You'll also notice that there's a very small drop in the output voltage, which is a feature from the R out, or the natural impedance of this transformer. We'll go on to use that in some of the features later. So we've now introduced two components, the non-isolated buck boost and the sine amplitude converter, and we can now put those in different arrangements to have different end application solutions. In a traditional converter, like a forward or a flyback or a full bridge, the function of regulation and transformation are bonded together in the same way. So you have the same frequency of switching, you have everything entwined, which means that if you want to improve part of that, maybe improve the regulation or improve the efficiency of the transformation, it's very difficult to do because you have a single block. But if you were to separate, or in Vicor we say factorize, into that separate element of the separate regulator and a separate transformer, these separated or factorized building blocks are the Lego building blocks that we use for the systems. In this way, if we want to use a next generation MOSFET from one of our suppliers, maybe increase the frequency of the transformation stage, maybe change the regulation accuracy of the regulator, we can do that independently, and they still are very high performance building blocks for the system. So in a full power supply, of course, you usually need transformation of voltage and also regulation of that voltage. So how do you do that? With a buck boost regulator and a transformer. The simple answer is that the regulator is the brains of the outfit. So if we adjust the regulator, we can take in our varying DC input, in this example 38 to 55, and stabilize that to a 48 volt point. Now the point between the regulator and the transformer we're referring to as the factorized voltage, or VF. So in this case we're setting that at 48 volts, and then we're letting the downstream transformer simply do its job. In this example we're using a 1 divided by 4, or K factor of 1 over 4, to take that 48 volts and create 12 volts. If you want to reduce that output voltage or increase that output voltage, you adjust the entry point to the regulator. So by changing a resistor or a PWM entry to that regulator, you adjust the VF, the factorized voltage, leading into the fixed ratio transformer. So in this way, the regulator is the brains of the outfit, the transformer simply does its job. And obviously we have different transformer ratios, anywhere from 1 over 1, which is an isolator or voltage inverter, all the way to 1 over 40, so a very high transformation ratio. Now we also need to be concerned about regulation, and in this kind of system we have 3 options depending on the regulation required and the components to do that. The first one is where we have a very, very simple regulation where the regulator looks simply at its own output. That's the local loop. Very, very simple circuit, gets to about 3 or 5% regulation over line and load. If we're looking for a little more than that, we can take a measurement from the transformer itself, which is a little closer to the load, and we call that the adaptive loop. And with adaptive loop, we can get 1 to 2% regulation. And if you really want the tightest, we're down at 0.2% regulation with a remote sense system. Again, feeding back from that point to the regulator to control that intermediate voltage. Regulation obviously is a very strong point for us, especially when it comes to things like processors. So a slight detour into the lower voltage world, this is showing that obviously Intel and other companies have very strict regulations on how we control the voltage going into their microprocessors, and also how stable we need to be under transient conditions. So these are just a few photographs of VR, that's voltage regulator test boards for the various Intel options. In this kind of application, the processor gives out a signal, or an SVID, which is the Serial Voltage Identification Command, to the power system to say either ramp up, ramp down, go into energy saving states, etc. So what we do in this kind of system is the Vicor components act as a pure, very efficient, very small size powertrain, and we use a third-party SVID controller to take that command from the processor and create a signal for the PRM to control its voltage. So a very simple system and a very dense and efficient system as well. Now, back to some of the features of the sine amplitude converter, especially when we're focused on transient performance. So normally when a load goes through a transient step, so your laptop wakes up and suddenly you're playing Halo 5 with 10 of your friends around the world, you have a huge draw of power in the form of current, and what we need to do is control the voltage and keep it as stable as we can during that power transition or that current load step. So normally there are large bulk capacitors placed at the load itself from which to draw power and maintain that stable voltage. So those capacitors are located at the, for example, 1.5 volt rail. Now, we all know that the energy stored in a capacitor is proportional to the square of the voltage. So at 1.5 volts, that's not a lot of power. However, the sine amplitude converter has a very low impedance. So if we take a look at the 1 divided by 32 example, it has less than 1 milliohm of impedance from DC up to 1 megahertz. This means that when the load goes through a transient step, it can see through the transformer and up to the higher voltage rail. And if that rail is at 48 volts instead of 1.5, we can take the proportion of those voltages, which also is the simple K factor of the transformer, squared, and use that as a reduction in the number of farads required to do exactly the same purpose. So in this case, with 1 over 32, we get 1,000 times reduction in the amount of capacitance required. Now, also by going from very low voltage up to large size caps to a much smaller value, we can also change technology from, say, electrolytic or OSCON capacitors down to very small surface mount ceramic chip capacitors. So we have a benefit in size and cost, and to some extent efficiency, and depending on your ambient conditions. Another benefit of the sine amplitude converter, using the fact that this is an isolated converter, means that we can stack. We can stack the inputs, and the top two drawings are basic schematics for, on the left, a 48 volt input device, which happens to have a full bridge on the primary. On the right-hand side, we see stacked half-bridge cells for our 380 volt DC input converters. So you can see that by having this stacking performance, we can increase the voltage to which we can address the component. One of the other things about this stacking, and also part of the zero voltage switching, zero current switching techniques, is that we can use, for example, stacked 250 volt MOSFETs on the primary side of our 380 volt input units. And as the resistance of a MOSFET, that's the RDS on, is related to the difference in voltage to the power 2.5, it means if we go from, say, using a 600 volt FET in a hard switch topology to the 250 volt FET in this stacked zero voltage topology, we are, trying to do this in my head, 600 for about maybe 9 times lower in RDS on. So we can have a huge saving. Also, the QGD usually follows in the same way. So using higher performance MOSFETs, we have that higher efficiency, higher switching frequency, and that positive spiral. So that's stacking the inputs. On the outputs, this drawing is from the DC components and grid team, where they are using 2 of our bus converters with a K of 1 divided by 32 to go from 384 down to 12, but then they're stacking the 12 volt outputs to get 24 volts for a nano grid within a room, let's say for LED lighting. So this is the ability of the sine amplitude converter to stack inputs or stack outputs. Now at the same time, we need to look at paralleling for higher power. So here we're looking at a couple of examples of paralleling the sine amplitude converter. And we go back to that R out, or that natural impedance of the device. The sine amplitude converter has an impedance with a positive temperature coefficient. This means that an array of sine amplitude converters acts like an array of resistors. If one of them takes too much current, the temperature increases, the impedance increases, the current is naturally reduced. So a very simple way of using components in parallel for high performance, high power, with no interconnect, no command and control required. So a very simple system. The photograph on the top right is a look at the IBM Power 7 IH DCA. This is a DC assembly. This whole unit takes 350 volts DC, and part of this board uses 54 of our bus converter modules using the sine amplitude converter to convert from 350 down to 44 volts. And this is a 20 kilowatt unit. So you can see very high power systems can be built up using these Lego bricks. One of the other benefits of having these components, these Lego bricks, is that in large systems we can shed power, or rather shed components, if we don't need full power. So much in the same way as we could have a multi-phase sync-buck converter and phase shed in light load times, here the eco array shows that if you want full power, okay, turn on all of the BCMs in that array. If you don't want full power, just turn on 1 or 2 or 3 of the converters to improve the light load efficiency. So here we're looking at paralleling and the ability to turn off devices if you don't need that throughput. Now, reversibility is a fantastic feature of transformers. So in this case, the first thing is we need to stop thinking about primary and secondary, because we could talk about left to right or right to left. So for example, if you have a 1 divided by 4 transformer and you put 48 volts on the left, you'd get 12 volts on the right. Using the same thing, if you put 12 volts on the right, you would get 48 volts on the left. So you can transform down and also transform up voltage. So various uses for this. The first one on the left-hand side is an example where we have a 48 volt rail and we're using a 12 volt battery as a backup. So in this case, we're using a single regulator at 500 watts with a 1/4 transformer to regulate charge going into that battery. If the 48 volt rail was to go away, then that 12 volt battery is now stepped up using the transformer running in reverse and regulated, in this case using 3 of the regulators to make 1500 watts back to that 48 volt point. So this is an example of reversibility of the sine amplitude converter. And again, also the discrete factorized building blocks, those Lego bricks, which mean that you can size the powertrain for your needs. So we only need to charge at a lower rate, so we can use a single 500 watt device. But when we need the power, we need all of it now, so we have 3 of those guys for the 1500 watts. On the right-hand side, this is an earth-moving example where there is a generator which creates 800 volts with a center tap. And we can stack our high voltage bus converters with using that virtual ground to use 400 volt devices stacked to reach an 800 volt system. In this case, we use the diesel engine creating that 800 volts to charge a 24 volt battery, and also we see an auxiliary 24 volt load. But also, if you are operating your bulldozer or your digger in the desert and you want to stop for lunch, then you want to turn off the diesel engine and save fuel. But you still want your air conditioner to run. So at that point, the battery goes and using the bypass diode in this case, because we don't need tight regulation for this kind of load, creates back to that 700 or 800 volt rail to run the air conditioner. So another example of stacking and also reversibility using these two building blocks. We do have a full technical paper on this. However, it's actually been accepted at the APEC conference for next quarter. So as soon as it's available, we'll have it for you. In the meantime, unfortunately, it is embargoed. Now, if we have a power system which requires regulation, and we regulate all of the power all of the time, it can be very inefficient. So, for example, a traditional forward converter, you're regulating all of the power all of the time. But we have two examples using this factorized building block approach where you can beat that challenge. So the first one is called the Yeaman topology, named after the director of the VI chip applications team, Mr. Paul Yeaman. He came up with an idea where you only regulate part of the power all of the time. So in this case, we're paralleling some big bus converters to go from 350 down to maybe 10 or 11 volts. Remember, that's a fixed ratio, unregulated converter. But we are stacking on top of that a regulating voltage. So here we have, you can see that the mass of power, or the majority of power, is bus converted down to 10 or 11 volts. But then a much smaller set of it, the minority, is truly regulated. But by stacking those outputs, we have a total regulated output. So we have very high efficiency through those bus converters, and then we only regulate only enough power to get the regulated output. The photograph at the bottom comes from the IBM Power 7 IH disk array power supply. So in this IBM Power 7 system, they have racks of processors and memory, and then separate storage racks containing disk drives and also tape systems. So in this case, we are bus converting a huge amount of power using paralleled bus converters, and then we have that additional regulating stage. This example is a 9 kilowatt conversion, and it reaches a 38 watts per cubic inch power density. So you can see a very, very dense, high efficiency system. And this was using the components that we had available in 2009-2010 timeframe. And obviously with the chip technology, we will be improving on these specifications. So with the Yeaman topology, we regulate some of the power all of the time. In the equalizer topology, we regulate all of the power, but only a very small amount of the time. In this example, we're looking at the ETSI input range for a data center, which normally runs at 380 volts, very tightly controlled. In that case, we simply bus convert down to 48, and we have a very high efficiency system. However, in cases where that voltage drops, we can then introduce our buck boost to regulate back to that 48 volt point. So the majority of the time, the 99.999% of the time where we've got 380, we have the highest efficiency possible, just bus converting. But on those stages, those times where the voltage does drop, the regulator kicks in, keeps everything nice and stable. So in this example, we're regulating all of the power, only some of the time. Putting a few of those things together and looking at the 2x overpower capability, this is a powertrain. We'll be going into more detail in the airborne applications for commercial and military aircraft. This is going from 270 volts DC down to a transmitter. In this case, we're choosing a 2.5 volt silicon germanium transmitter for a radar application, noting that this is a pulsed power application. In this overall system, we are bus converting and then regulating to charge a large cap bank, and then we are taking the energy in that cap bank in pulses to the transmitter. So a few features here. Obviously, we are paralleling bus converters and regulators to get to the right amount of power to trickle charge or average power charge that capacitor bank. Downstream from that cap bank, we are using only enough bus converters to provide that 2x power capability we need. And that's 2x power capability because the sine amplitude converter is a thermally not power limited device. So by allowing this to run at a pulse duration or by maintaining the case at a low temperature, we can get more power out of this DC to DC transformer. This diagram also shows that we can do the capacitance elimination technique, and in an airborne application, size and weight are critical factors. So using all of these things together, paralleling where you need to, using the 2x overpower when you can, using that capacitance elimination technique, plus also having high efficiency building blocks to cut down on the amount of heat sinking required, we can get down to an 8 or 10x reduction in size and weight, which obviously is key for airborne applications. Now, today, if you'd like to, you can go to vicorpower.com and look at our tools section, which we call our PowerBench suite. We have some very powerful tools online, first of all, to select the right components if you need to, and also to configure them in different ways if you need a customized product in real time, to place them on what we call a virtual whiteboard so you can see how things fit together and run scenarios to analyze system efficiency, and also to do simulations of the different components. So, for example, on the bottom left here, we have a simulation of bus converter. We can run thermal as well as electrical simulations like steady state or enable or load step. So all of these tools are available online, and I would encourage you to please go to the PowerBench suite and take a look at these, and I think you'll be very impressed. We will be using these tools during the application and market-specific topics to show the changes in efficiency or the size or how the systems are set up. So that was a look at the two building blocks, the PRM buck boost unit and also the sine amplitude converter DC to DC transformer. So that was part 2 of our seminar series. So we have the introduction, we have the technical deep dive, and then we will be going into application and market-specific sections. And very happy to announce that we have 2 guest speakers so far on this series. The first one will be on the first market-specific topic, that's the 380 volt for data centers. We have Mr. David Moore of HP from Houston, Texas, who will be taking us through his Intellect paper from 2013. And due to some requests from the first seminar, largely based around ducting, busing, arcing, safety aspects for the infrastructure of high voltage DC, we have Mr. David Geary of Universal Starline who will do a guest presentation. We've squeezed in the infrastructure presentation, so the dates on the other ones have shuffled backwards a week, so these are different to the dates that we had last week. But we will be sending out email invitations to remind you of dates and times.